Hey everyone, this is Doug. Today I'm just going to walk you through how to quickly set up a sample case using Optix. So I've downloaded Optix here, version 1.0. By double clicking, it will open that in a new folder with all of the files extracted. You'll see that there's only 4 files in here. Optix.out, which is the executable. There's a README file, a sample function, which we'll get to in a second, and then a start.json file, which is basically all of the commands for Optix. So I'm going to start a new working directory here called test case. And in order to run Optix, this executable needs to be in my path. So there's 2 different ways to do that. I can either copy that into a folder that's already in my path, or I can copy it into my working directory. So I'm just going to put it in my working directory today, and I'm also going to move in the sample function and start.json files. So those now are all inside my working directory. And let's start with the start.json file. This file basically is all of the commands for Optix. So it has 4 main objects within it. The start file is set up as a JSON object, and within that it has 4 objects. It's got settings, variables, a run commands, and then interface. So the settings section you probably won't need to change very often unless you know what you're doing. That's basically telling Optix what kind of differencing schemes to use, how big of steps to take, and how many simultaneous cases it can run. So this end search, we have it set right now that it can run up to 16 cases simultaneously if it needs. We have this variables object here defines the variables that we actually want to optimize. So today we're going to do a very simple function that's just a function of 2 variables, which we're calling x1 and x2, and I can just put the name of the variables right in here. Each variable has an init value, so we're going to initialize x1 to -3, and then we're going to set this setting called opt to on, meaning that Optix can change that variable. If I turned this off, then it would hold x1 constant at -3. So x2 we're going to initialize to 1 and also allow Optix to change that variable. This next object is called run, and run is basically a command that Optix is going to run in order to run each of these test cases. So today we're going to work with an executable called function.out, and we'll get to that in just a second. But for each case, Optix needs to run function.out, and then this function is going to return a file that Optix will read, and that's defined here in the interface section. So the interface section has 2 components here: variables, which is assigned vars.text right now. That means that for each test case, Optix is going to write a file called vars.text that has values for x1 and x2 inside of it. And then Optix is going to look for a fitness.txt function, or excuse me, a file to appear. So the order of operations here is Optix is going to choose values for x1 and x2. It's going to write those to vars.text. Then it's going to call this run command. And after it calls the run command, it's going to wait until it sees this text file appear, fitness.txt, and it's going to read the value from fitness.txt as the fitness function for that set of variables. Okay, so that's the basic interface to Optix there. Today we're going to be running a sample function, which I've written in Fortran here, but you can use any code. You can anything that you can call from a command line here. You can use, but today I've written this in Fortran, and it's just a pretty simple code here. We're going to define 3 variables here: x1, x2, and fitness. We're going to read variables x1 and x2 from vars.text. Then we're going to calculate fitness as this function here, and I just put in a parabolic function. It's pretty simple. And then we're going to write the value of fitness that it calculates, which is a function of these variables here. It's just going to write those to a file called fitness.txt. And I'm writing this out actually at pretty high precision here. You want to make sure that you have high precision in the values that you're passing to and from the optimization code. The higher the precision, the more accurately Optix can find the optimal value. So we're going to pass in, you'll see here, 16 digits of fitness, which is machine precision. We're passing in as much as the computer knows about that value. Okay, so I have my sample function code set up here. I'm just going to go to a command line, and we're going to cd to my working directory, which is the test case. And now I need to compile my F90 code, so I'm going to do that with G Fortran. I'm using double precision here, and I'm just going to compile sample function.f90, and I'm going to have it output a function.out. This is the executable that it's going to build, which is the executable that Optix is going to call here. Okay, so function.out now is in this directory. And one thing that's important to know about Optix is that for each case, it's going to create a brand new subdirectory within this working directory. So we're working inside of test case here, and inside of this, it's going to create directories, and each directory is going to be a single case that it's running. So when it runs this code, this function.out code, it's actually going to be running from a subdirectory. And so in order to call the function.out code, I have to do the .. slash here. That takes me up one directory, and so I'm telling Optix you're going to find function.out up one directory from where you are. And to keep things simple right now, I'm going to take off this ampersand. The ampersand allows Optix to run in parallel. You just put a space ampersand at the end of that line there, and it will allow Optix to kick off more than one case at a time. However, today we're just going to keep it simple and just run one case at a time. Okay, so we should be all set up here, so I'm just going to call from my working directory here, I'm going to call optix.out, and then I'm going to pass in the start.json file there on the command line, and just push enter. Okay, and it says optimization complete. If I scroll up here, we can just quickly walk through what happened. So it read the start.json file. It says it's going to run this command, the function.out. It's starting with x1 and x2, initialized to -3 and 1. Gives us a copy of our settings here. And then it begins to optimize. This first line here is before it runs any iterations. These were the value of our variables. So we had a -3 and a +1 and a fitness value of 19. If you plugged in the -3 and the +1 in our function, we'd get a fitness value of 19. And then it's just going to show us the iterations that it went through here, the change in the variables as it went along, and the fitness value. Now the optimum value of this function happens to be 0, 0, which would return a value of 0. So it's kind of a useful case because we know exactly what the optimum is. And you'll see that when this fully converged here, we got a value of 0, 0 to machine precision here. E to the -15 and e to the -14 is 0 to machine precision. And a fitness value of e to the -27, which is also 0 within machine precision. Okay, so that's just a real quick overview of how to run Optix. One last thing, maybe I should go through these, the files that I created here in this directory. It will leave one directory or one subdirectory inside of our working directory, and this subdirectory has the final version. So these were the final vars that it used, that vars.txt, and this was the final fitness value that was returned. It also creates some other files in here. So we've got a BFGS start and end file. This start file is simply a JSON file that shows us its initial values. Here's an end file, shows us where it ended up eventually. And then we also have gradient and optimization files here. This optimization is simply a history of optimization. These are each of the iterations that are made, the fitness value for each, and the variables for each. And then we also have a gradient.txt file, which shows us the gradient. Since this is a gradient-based optimization code, it shows us the value of the gradient at each of these iterations. Okay, I think that's it for now. Please leave a comment or let me know if you have any questions. I'd be happy to answer them. Thanks.